This video is going to be on strong acid, strong base pH titrations. By pH titration calculations. And it is the exact same example that I did in class, so maybe you want to hear this over again, or maybe you missed it that day. So I figured I'd just do a quick video on this one. So in this example, we have 40 milliliters of 0.100 molar HCl, and it is titrated with 0.100 molar NaOH. So for this system, you have a beaker or a flask, and that is going to contain your HCl. Then there is a burette above it delivering sodium hydroxide, and the sodium hydroxide is neutralizing the H plus from the HCl in solution. So let's see, we will start with the first step, which is 0.00 milliliters of sodium hydroxide added. Now that means that no sodium hydroxide has been added from the burette, and we just want to know what the pH is for the HCl. So it's very simple. It is going to be, since HCl is strong, so HCl is a strong, acid. So therefore, 0.1 molar HCl means 0.1 molar H plus, because there's 100% association. So it's already in molarity. The pH is equal to the negative log of the molarity of the H plus, so it's just going to be 0.1 here. And then log of 10 to the minus 1 is -1. Multiply that times -1, and that will be equal to 1. You can put some zeros in there. So that's the first step. Then the second step here, now we start adding sodium hydroxide from the burette. So you have 20 milliliters sodium hydroxide added. And it's kind of easy to visualize here because the concentrations of the acid and the base are the same. So we're going to do a reaction first, reaction table, stoichiometry table, where HCl and sodium hydroxide react to form H2O plus sodium chloride. And before reaction, after reaction, before the reaction, we have, let's see, the HCl. We should have calculated the moles first, so let me put them in here. Moles HCl is going to be molarity times volume. Molarity is 0.1, and then the volume is 40 milliliters, or 0.040 liters. So this is 0.0040 moles. Now in this step you have added some sodium hydroxide, and that is 20 milliliters. So that's going to be 0.1 molar times 0.020 liters, which is 0.0020 moles sodium hydroxide. So those are the numbers. I should have done that before I put up the reaction table. But those are the numbers that we're going to put in this table. So the HCl is 0.004 moles, and the sodium hydroxide is 0.0020 moles. For the reaction, you don't care about the water. We start with 0 sodium chloride, And then we have the sodium hydroxide being the limiting reactant, so you want to subtract those moles from both of the reactants. This is the amount that's used up since it's a 1-to-1 reaction. And then we're going to get here 0.0020 for the HCl, and the sodium hydroxide is 0. We have 0.0020 sodium chloride that's been produced, and that is there as well. So then you ask, what kind of solution is this? The sodium chloride contributes nothing to the pH. It's neutral. Remember, it's a salt that comes from a strong acid and a strong base. So it's the HCl that remains, and you have 20.002 moles of it. So to get the pH will be negative log of the H plus concentration. So the H plus concentration is going to be the 0.0020 moles that were just left over after the reaction. And then you want to divide by the volume. You started with 40 milliliters of HCl, and you've added 20 milliliters of sodium hydroxide, so that's 60 mils. So this is 0.060 liters. So the H plus concentration will be, let's see. I don't have it written down, so I will calculate it. 0.002 divided by 0.06. So this is 0.033 molar. All right, so pH then will be negative log of that. And that works out to be 1.48. I just checked that. Yep, that's right. Okay, so that's the second one. Then our third calculation will be associated with adding more sodium hydroxide from the burette. So for the next step, it's going to be 40 milliliters of sodium hydroxide added. Now think about it. In part 1, there was 0 milliliters added. In part 2, 20 milliliters were added. And now part 3, we have 40 milliliters added. We'll call that part C. 40 milliliters added. And the 40 milliliters means that 20 had been added from the last step, and now you added another 20 to have a total of 40 milliliters. So this right here is the total volume of NaOH. So that's just a point you don't want to confuse for that. It's not that you have 60 because it's 20 plus 40. It's 20 plus 20 makes 40 total for the step. All right, then we're going to do another reaction table. You have HCl plus sodium hydroxide forming water plus NaCl before reaction, after reaction. And in this case, you have sodium hydroxide is 0.1 molar, so 0.10 molar times 0.040 liters, 0.0040 moles NaOH. I should have done that before. So now you have 0.004, 0.004, and 0. And you can see the moles are equal, so you've reached the equivalence point for the system. Both the HCl and the sodium hydroxide are completely consumed, and the only thing you have left is 0.004 moles of sodium chloride. So you could try to do a negative log of that, but you can't because it's not an H+. This .004 is just the salt, and it happens to be a salt made from strong acid, strong base, and so the pH here is neutral. No effect on the pH if there's NaCl present. So you're good. You can stop right there and just say pH is 7. If you want a little bit more detail on this, remember pure water has 1.0 times 10 to the minus 7 molar H plus and 1.0 times 10 to the minus 7 molar hydroxide. And the product of those two is Kw. So if this is the case here, right, you could say pH is the negative log of 1 times 10 to the minus 7. pH is 7, so you could get it that way if you thought about it deeply. So that's the endpoint or the equivalence point. And for the case of the strong, the pH is going to be 7 at the equivalence point. All right, then the last part here is 50, call that part D, 50 milliliters of sodium hydroxide added. Of course, that's the total amount. Go back to your reaction table, do another one, and this will be HCl plus NaOH forms H2O plus NaCl. Before the reaction, after the reaction, 0.0040. With 50 mils, if you multiplied that times the molarity, you'd come up with 0.0050 moles. So in this case, the HCl becomes the limiting reactant. We have not seen that before. No big deal. Oh, wait, gotta add over here. So then you have 0 for the HCl. The difference here is 0.0010 and 0.0040. So this does not contribute to the pH. Again. Instead, we're going after that. This is going to be related to the OH minus concentration. So we'll go ahead and calculate POH. That'll be the negative log of the concentration, which is 0.0010 moles hydroxide, divided by the total volume, 40 milliliters of the HCl, 50 milliliters of the sodium hydroxide. The total volume is 90 milliliters or 0.09 liters. And calculate that too. 0.001 divided by 0.09. So that is the negative log of 0.011. And that is equal to 1.95. So the POH equals 1.95. And now we can get the pH, 14 minus 1.95. And this is going to be equal to 12.05. All right, so we saw what happens after the equivalence point. The pH increases dramatically. So if we made a list here of our milliliters NaOH added, and then the pH, you had 0, 20, 40, and 50. The pH was, let's see, this was 1. At 20 mils, it was 1.48, so not a big change. At the equivalence point, it's 7. And then past the equivalence point with 50 milliliters, it's 12.04. So huge differences there. 5, sorry. I had 4 from another calculation. So last thing is to graph it. And the graph will have volume, milliliters of NaOH added. So you have 0, 10, 20, 30, 40, and 50. pH goes from 1 to 12, so I don't know, 2, 4, 6, 8, 10, 12, 14, something like that. And the first point is 0, and the pH is, sorry, that's, hold on, this label is going to 2, 4, 6, 8, 10, 12, 14. So, let's see, do a different color, blue. At 0 mils, excuse me, the pH is 1. At 20 mils, the pH is 1.48, so really no big change at all. Suddenly at 40 mils, it pops up to 7. And then 50 mils, it's all the way up to 12 something. So it looks like almost like an exponentially increasing function, but if you had more data points, you would see that the curve looks like that. And this right here is the equivalence point. And graphically, I don't know if you did this in the lab or not, but you could draw lines like this, measure the height here, cut it exactly in half to get your endpoint, come down and get your volume, come across and get your pH. And so that might be like a laboratory evaluation of that. In any event, it's very different from strong weak or weak strong because this region in the middle is very steep, and also the ends are more extreme than for the other case. So, all right, thank you. That's the end of that one right there.